When you're learning design in Verilog, it's really tempting to focus on the design itself, looking at your design modules, your inputs, your outputs, and getting something to synthesize in Vivado. But here's the truth. A design that hasn't been tested is not really a finished professional design. In real engineering practice, most bugs aren't caught in hardware, they're caught in simulation. And the tool that makes simulation meaningful and practical and possible is the Verilog code that surrounds your design in simulation. It drives inputs, observes outputs, and checks whether the design behaves the way it should. And the better your test bench is, the faster you can find problems, fix them, and move on with confidence. Now, when students first start writing test benches, they often treat them like, oh, here's a one-off, let's just go through a few inputs, see what happens. But really, you need a more systematic way. As designs get more complex, the approach breaks down pretty quickly. And if you're relying on just doing a few test inputs and looking at the waveforms, you definitely want to get away from that when you do more complex designs where you can do automatic verification of designs rather than having to manually check things every time. That's why test benches tend to follow a standard overall structure, and learning that structure makes it easier to know how to make test benches that become much more sophisticated. Most Verilog test benches include the same core pieces, and so we're going to do a very simple test bench on the simplest thing I can think of, and that would be an AND gate. So we're going to break these into core pieces. So the first thing we're going to look at is the signals, how you control the things that go into your test bench, how you instantiate the thing that you want to test. All test benches are going to have an initial block, a starting point as to how we run the simulation. Within that starting block, we have to generate some test vectors to make sure we see, test what's happening. And then the best test benches have some way of doing automatic verification that your design works. You know how your design is supposed to work. You need to put that into your test bench. So we're going to go through this in pieces with a very simple example, and then hopefully you can start to wrap your head around what's involved with making test benches. So first up in generating a test bench is the declaration of the module and defining the signals. So typically we give this timescale parameter. We'll talk more about this when it becomes more relevant later in the course. But you start with defining a module name, and typically the module name fits the module that you're testing with the additional modifier that you put the TB to make sure that you know it's a test bench. From there, we need to instantiate the signals or generate the signals that show up in the test bench. So if you're going to try to control something, typically if you're doing a test bench, you have inputs, you want to control the inputs. So we drive the inputs. Because it's something that we're trying to control, you need to have this a parameter type as a reg. Okay, so we're going to control the inputs A and B are scalars. If it's something we're going to observe, it's a wire. All right, so that's the part of the unit under test. We have two inputs, A and B, and the output Y. Now to make this test bench self-checking, we're going to add another wire that we're going to call the expected, and we're going to control what the output of that wire would be within the test bench. Okay, so expected is something that we're going to use for testing of the test bench. Along the way, we might have some variables that are involved because this is a simulation, this is not hardware. So you can use some programming like variables to help your test bench, track things along the way. So for example, if you find an error condition, you might want to count how many errors there would be. So you can make a programming like thing called error count in this case to help you keep track of errors. Next up is instantiation. So once you have the signals defined, the next block within a test bench is the instantiation. So we've talked about instantiation on the RTL or the design side. It works exactly the same way. You have already defined the input signals, those are A and B and the output Y. That's involved with the unit under test. And so You do the normal instantiation, AND gate, identifier, start the module instance in the module instance, and then .a, the input condition .a connects, or that the port .a connects to the register name. In this case, we name them the same thing. That's common because it prevents confusion, and it's pretty fast to name your test signals the same thing as the ports on your test bench. So .a connects to A, .b connects to B, .y connects to Y. We have now instantiated the unit under test. That's an easy step to forget because it seems obvious that you want to test the AND gate, but the test bench needs to know that, so you have to instantiate it to make it happen. Next up is putting in the initial block so that you can actually run the test vectors. Now later on with Verilog, we're going to learn about an always block. With the design, there's certain behavioral things that are always happening with the design. But with a test bench, you actually want to run through a sequence of things just one time, and that's what an initial block is for. Okay, so with an initial block, you start with the keyword initial, and then if it's only one line, sometimes you can have an initial block that's only one line of code. But if it's more than one line, you need to tell it which lines apply. So we start with a begin and end with an end. So everything else is part of our test bench. So in this particular case, what we're going to do is we're going to start with zeroing out the variable that we defined for the error count. And then we're going to have a way of writing back to the console, the tickle terminal, and Vivado, for example, is one thing you could use with a $sign. So a $sign is a system task. One of the ones that we can use is just display. Okay, so it displays the text testing ... to let you know that, oh, I'm starting to run the unit test. At the end, you need to give a system command $finish to let the system know that we're ending the simulation. In the middle part, we'll talk about this next, is where you put the test vectors and the ways to report the results. Okay, next up is generating the test vectors. So let's move to this stage. In this particular case, we have a very simple circuit. It's just an AND gate. And with an AND gate, we have 4 input conditions, and so we can exhaustively test those. All right, so you could use a for loop, and that would be an advantage if you had a lot more input conditions, but I want to keep this simple. Let's talk about how you would generate the test vectors. Okay, so you notice here we're going through the combinations A equals 0, B equals 0. We can use this notation. The curly brackets means concatenate, so we're going to take 0, 0, and concatenate that together into A and B. All right, so it's a fancy way of assigning A equals 0 and B equals 0 using the concatenation operator. This is a super useful thing to use in Verilog, and it's something you get tripped up on initially. So concatenation, set both inputs in one statement. The next important thing is the idea of simulation time ticks. All right, that's what the pound notation tells you, and that's followed by a number. So we're going to go through 10 simulation time ticks. We could have just done 1, but 10 in this case. Maybe you have a little better waveforms that get generated if you're using the waveform generator. So that's why you go with a larger number. Okay, so pound 10, we're going to hold this input combination for 10 simulation time ticks. And then later on, when we get to the verification step, there's basically a subroutine or a function that checks the output to see if it's right. Okay, so you see this part in green. We're going to do an experiment on GitHub where you're going to make your own test bench. This is a part that you need to complete. The same thing, I forgot to say that for the signals. For the example that we're going to do on GitHub, you have to complete these parts in green. Okay, so I think at this point we have test vectors determined, and we'll be ready to look at the next stage, which is verification. Okay, so in the verification stage, we need to look at this subroutine in in Verilog, it's a task, and we name that check output. Okay. Now, we have already set up a wire for the expected output. Okay. And so we know that the expected output is A and B. Now, I agree. In this case, this seems trivial because the design statement is the same thing. But in general, there's an abstraction level where you know what the expected output would be. So you're making a comparator. You would know, with a C-like command or a MATLAB-like command, you could test whether A is bigger than B. But your circuit design actually might be logic equations that implement the comparator. And so those aren't the same thing. Logically what expected should be might be different than how you implement that with a circuit. So if you can take the logic of what you're expecting and compare that to the hardware realization, that's why this makes sense. Okay, so you have two different ways of verifying things. It's what your hardware produces and also what you logically expect. Okay, so it makes sense here if y is not equal, so exclamation point equal means if these aren't the same, then we're going to display fail and we're going to increment the error count. So we'll know how many errors that we have. And then end. All right. So if y is not equal to expected, it runs this part. Else, it says that it passes. Okay. And so that's the testing loop that's in this particular test bench for the AND gate. So over here, you could take a look at how this is working just to help you conceive of what's going on. We're going through all the test conditions. So if we were testing this with a correct design, what should happen is when I hit test here, I'm going through all the input combinations. I'm checking, is y equal to the expected value? If it is, it passes and the errors are 0. If you had a buggy, if somehow you put in an OR gate instead of an AND gate, all right, you would run through the input combinations and there'd be combinations where it doesn't match and you would get an error count that lets you know what's going wrong. Okay, so that's the basics of test benches. I'm going to give you a GitHub assignment where you can work through this. Notice you don't have anything to do in the verification step, but in the signal step, you'll need to implement the signals, set those up as regs, set outputs up as wire, set up an expected signal, maybe have an intermediate variable. For instantiation, you have to instantiate your design like we've talked about several times, set up an initial block. That's going to be done for you, okay? And so we'll have that and you'll input the test vectors into the next step. So you go through all the combinations of inputs. And then the last part is you'll have a verification code that you can look at. You don't have to do anything here, but you'll be able to run this in the GitHub experiment that accompanies this video.